Ist das plötzlich nicht mehr. Wofür die oh, Mensch. So welcome everybody for our afternoon session here in information theory and coding. Also welcome to the students from Kazan and other countries. So let me see what we do today. So last time we talked about the analytical calculation of the bit error probabilities or estimation, approximation of bit error probabilities for the hard decision decoding case. Today, we want to have a look at the soft decision decoding case. This will be a bit more difficult from the mathematical point of view. We need to deal somehow with this Gaussian distributed noise process. So this is a bit more challenging. But I think we will get it explained well and nicely such that you can understand it. Okay. Before we start, we repeat briefly what we did last time. So we started by looking at how to calculate bit error probabilities for certain coding schemes. So always, just for simplicity, we use this repetition code as example. We could use any other coding scheme, but this is the most easy one to imagine and to have a look at all possible cases at once. So if we would use a code with code word length 7, would be quite hard to write examples. So this very simple code used here. And we had a look at now the cases where things go wrong, so where our decoder will not be able to correct the errors. Because this will be the case if we transmit a 1, 1, 1 and we receive a 0, 0, 0. If our receiver, our decoder, observes a 0, 0, 0, it will say probably 0, 0, 0 was transmitted, no error, no problem. But actually we transmitted a 1, so it would be a wrong decision. We would get a wrongly decided bit. So this is a case where things will go wrong. And we had 3 cases with 2 errors where we also will get a decoder. So if we have 2 zeros, our decoder will say, I see more zeros than ones, let's decide for 0. And again, we will get a decoding error. So the red and the orange cases, things will go wrong. In the green cases, only 1 bit being wrong, our decoder will decide correctly and the transmission error will. So we need to worry about the red and orange case. And we tried to describe this in equations. So we noticed that obviously the distribution of errors inside a code word plays a role. So bringing it to the question, how can 2 errors or how many combinations can we get with 2 errors in a code word of length 3? And to describe this more general, we use this binomial coefficient. This basically gives us the number of combinations. Are errors in a sequence of length n. And with this idea, we could come to a general description. Because we need the number of bits that can be corrected. In our case, 1 error can be corrected. If we have t plus 1 wrong bits, things start to fail, and we basically just wrote down this probability that we get a wrongly decided code word. Here the orange cases with 3 combinations with 2 bits being wrong, meaning 1 bit correct. Here things will go wrong. And we have 1 combination with our 3 bits being wrong. That will happen with probability PE to the power of 3. So, and then just extending our specific example to the general case, obviously this is straightforward then. We start to get errors from t+1 wrong bits, get decoding errors. Then we have n over r combinations, how r bits can be wrong in a code word of length n. And here the probability for the r wrong bits, and here the probability for the n minus r correct bits. So this is just a general formula describing what we figured out before, looking at our simple example. Okay, and then we started to simplify things again by using some approximations. So for example, if we assume small values of PE, these higher powers of PE become very small. So small that we can neglect them as compared to this, powers of PE. Just imagine again, PE, for example, 10 to the power of -3. So then this would be 1 out of 1,000,000 cases, and this would be 1 out of 1,000,000,000 cases already. So we just neglect the higher powers using only this dominant expression. And we also brought this to our more general formula. So then the sum simplifies to just the one case where we have t+1 errors in the code word. And for this, then using additionally this approximation, how to get from the word error probability to the bit error probability, which gave us a final result here, how to approximate the bit error probability. Then we also thought about how to calculate this error probability. For example, if we consider an additive white Gaussian noise channel. So there we found out that in this case, we get this Q function being integral over a part of this Gaussian distribution. Yes, so with this we could actually calculate how this bit error probability behaves as a function of b over n0. And I also have shown you some simulation results for advanced coding scheme, the 7,4 Hamming code, where we actually saw the performance of this one. And we could compare it with the approximations that we found. And then basically we continued to come up with equation approximation where we get an idea what we can benefit from applying such a coding scheme. So we asked for this asymptotic coding gain here. For high signal to noise ratios, what's the benefit of applying a certain coding scheme? So, and we got this by writing down the bit error probability for the uncoded case and for the coded case. And then we said, okay, let's compare both cases for the equal bit error probability and ask what's the difference in signal to noise ratio? What's the relationship between signal to noise ratio? And ended up with a fairly simple equation here, how to calculate this hard decision decoding gain. And we found out that, for example, our 7,4 Hamming code will give us a gain of approximately 0.6 dB at high signal to noise ratios. So that's the benefit of applying this coding scheme. But we could estimate it for any other coding scheme. You see, we just need the code rate and the number of bits that can be corrected. We could also express it in terms of the Hamming distance here, the minimum Hamming distance. These simple code parameters we get an idea of how powerful this code can be. Okay, are there questions? I think this was not so difficult. As I said today, it will be a bit more challenging. We look at the soft decision decode. So analytical calculation. Error probabilities. Soft decision decode. Okay, and I will start with a general model, what we imagine now. Imagine we transmit the sequence or the code word A, now actually mapped to plus minus square root EC. So here we have the coded bits inside, A0, A1, up to AN minus 1 code words of length n, and now mapped AI minus square root EC. Yeah, this is not so consistent in my lecture slides. So I use sometimes the code word A having only zeros and ones. Sometimes I use it as the mapped bits to plus minus 1, and sometimes to plus minus square root EC. To be more consistent, probably I should have used different variable names here, but if we write it down, we can understand. So, and then in our model, we add Gaussian distributed noise. So we have a noise vector here. Was also of length n, n0, n minus 1. Ni being from distribution with 0 mean and variance n0 half. Calligraphic n means normal distributed, so Gaussian distributed. Start with the Gaussian distributed. Mean value 0. And variance n0 half. So, and also the neighboring elements are statistically independent. So IID, independent, identically distributed elements here in this vector. So our code word to be transmitted, our noise modeled here as additive white noise process. And what we end up here is our sequence Y, A plus N. Quite a simple just for completeness, the vector containing the elements y0, n minus 1. So this is not very difficult. Let us look at an example where we will also model the noise process somehow with some numbers that we can calculate Euclidean distances later on. So example. I use the example from lecture slides, this 3,2 parity check code. Single parity check code. Just it's the n, k block code. So the code word length is 3, and we have 2 information bits here. With 2 information bits, I will get 4 valid code words, 2 to the power of 2. So this means we get 0, 0, 0, 0, 1. So these are the combinations how my information bits can look like. And if I encode this once, 0, 0, 0, we append a 0, 0, 0, 1. Get a 1 as parity bit, 1, 0, we get a 1. And here we have an even number of 1s, the modulo 2 sum will be 0. Those are our valid code words. Let's label them. So we start with A0. A1, A2. And I assume A1 should be transmitted for our example. Assume A1 is transmitted. So we map this. So here I also used a different mapping. I mapped the zeros to -1. But this is actually also not a problem. So the 0 to -1, +1. And for example, just for simplicity, square root EC shall be 1. Just to get some idea. So this is what I want to transmit. And I model also a noise vector n. I just came up with some arbitrary numbers like -0.7, 0.3. Random numbers now from a Gaussian distributed source. And you already see the thing that will be more difficult. As before, we had strictly binary values only, so it can either be a 1 or a 0. Now notice at the receiver side, vector y, now basically any real valued our real values can appear. So minus 1.7 here will make the first value minus 1.7. Second one will be 0.7. The last one will be. So this is what my receiver observes. And the question now is, if I observe these numbers here, I received sequence Y, which of the code words was most likely transmitted? The question is the same, just the way to answer it and to solve the problem is a bit more difficult as we have to deal with real values. Here basically, we need to answer the question, what? It's most likely transmitted. Chat. Yeah, okay. I was just briefly the question how I got the values from Y, but they already noticed it that it's just the sum. As we use this additive noise model, we just need to sum the values. Okay, so let us continue with our example. Just give me a note. Go back if I'm clear. So now the task is from our Y being 1.7, 0.7, and 1. Which of the code words is most likely transmitted? And we could have the following ones. A hat would either be -1, -1, -1, so the A0. It could be the -1, 1, 1. So any of the 4 could have been transmitted, the 1, -1, and finally the 1, 1, -1. Question mark here, so it's a good estimate. And we already thought about our decoding rule, about how to do maximum likelihood decode. We already know that we need to decode in favor of the minimum Euclidean distance. So the question is, again, pretty much the same as before. Before we asked which is the valid code word being most similar to what we received. And now the question is the same. Which of these 4 code words is the one being most similar to what I received here in the vector Y? And now most similar, the sense of Euclidean distance. So we need to add the Euclidean distances. So let me see, we write this as tabular form here. The Euclidean distance between Y and oh, yes, yes. Here we are. The other one is correct. Distance, we will this ones. So decoding in favor minimum Euclidean distance. So we need to choose our A hat such that the Euclidean distance between y and A hat is smaller than the Euclidean distance to all other code words for all B element and express this a little bit easy to understand. We find valid code word being most similar to the received sequence. Okay, so let's have a look at our example, how we do this here. G. Start with the Euclidean distance between A0, so the first one, and my received sequence y. So, and this will be like the square root. Yes, so to get the Euclidean distance, we need to subtract the individual elements. So we have a minus 1.7 minus the first element, this guy, is 1. Difference between the elements squared. Plus for the second one, we have the 0.7 minus 1 here. And for the last one, 1.2, again, minus 1. So notice the more similar these two vectors are, the smaller will be this Euclidean distance. The extreme case, if the values are the same, these differences will all be 0 and we get 0 Euclidean distance. If the derivations are bigger, this value, this Euclidean distance will be larger. So obviously, this is a good measure if we ask for similarity between sequences. So if we solve this, we get 0.9. If I calculate it here for the first one, I get a Euclidean distance between those two of. And we do the same for all other ones. A1, y. If we solve this, we get 0.8. And so on. 3.2 and 3.5. Well, and of course, we see it makes sense now to decide in favor of the minimum Euclidean distance. If we calculate all these distances, we will say, or we will see that this received sequence y has the highest similarity with code word A1, so probably a -111 was transmitted. Probably or most likely A1 is 1 was transmitted. To explain you this coding rule once more. So this just says we need to select a head estimate such that the Euclidean distance between my received sequence and the estimate I select finally is smaller than the Euclidean distance between my received sequence and all other code words from the set gamma. So this needs to be the smallest out of all of just this rule explained. Okay, so are there questions? I think so far it's not really difficult, but it's important that you understand this first before we go there a bit more into theory, because of course next will be the question, what's the probability that we make a decoding mistake there? Question, what's the probability that the noise gets so big that we will decide for another code word instead of the one that was transmitted? This is the more tricky question. Okay. See, also from Kazan, no. Okay. So let's start with thinking about cases where things go wrong. And there typically the so-called pairwise error probability plays an important role. It's down. Nice. This is a good point. Start here with the theory. Error probability. Sometimes also a previous PEP. And this is the probability that we actually decode code word, a wrong code word. So let's assume AI, code word AI is transmitted. What is the probability that it gets wrongly coded as code word AJ? Back to our example. I transmit code word A1. I can ask what's the probability that I will decode code word A3, for example. This could be in such a way that my received sequence will be more similar to code word A3, and I ask for the probability that this occurs. Here I also write one sentence more here. It's the probability. Is that AJ gets decoded instead AI. basically the same question, just expressed slightly different. It's good to write this still on this slide because here we have the decoding rule. So we basically ask for the probability that AI gets mistaken as a J. It's this notation here. And you notice this is the same as asking for the probability that the Euclidean distance between AJ and Y is smaller as the Euclidean distance between AI and Y. So distance between AJ is smaller than the distance between AI. Or again, explained more easily, the received sequence Y is more similar to AJ as it is to AI. My decoder will then, of course, make this decoding mistake. And now we ask for this probability. See, so here's a student question from a student. You are asking about this B. Yes. Here, I basically just use B to address all valid code words in this set of code words gamma. This set consists of all code words A0, A1, A2, and A3. So we could also say here, for example, vector AI, and then for I being 0 to 3. Maybe this would be more nice even. Yes, let me repeat it also for the students from Kazan. So here's a more general question related to the hard decision and soft decision decoding, why we use the one or the other. So we will see that if we use the soft decision decoding, we get some additional benefit. So we have more information because if you just look at the values, if I observe values here close to +1 or -1, I can be pretty sure that it was a plus or -1. So here, while processing this so-called soft values, I have some additional information on the reliability of the values, which is completely lost if I introduce somewhere a hard decision device, which just outputs a 0 or 1. But I have no information how reliable is this 0 or 1. So using soft decision decoding, we benefit from additional information which will yield a better performance at the end. And of course, you already see the price that we have to pay. It doesn't come for free. Whereas in the hard decision decoding case, we just needed to look at Hamming distances. So how different are code words? We could use an XOR operation to implement this efficiently. While here, if we would do the brute force approach, we would need to calculate, in our example here, 4 Euclidean distances, you see, with multiplications, additions, and other operations. So we have an increased computational complexity, but we get some benefit. Okay. So let's see how to continue with this probability here. So the pairwise error probability to mistake AJ instead of AI, AI, HA, so this way, AI gets mistaken as HA. And we already know this is the probability that, now I write it as difference here, minus AJ is smaller than A minus AI. And we actually know where our Y comes from. Y is actually what we transmitted, and we know we transmitted AI plus the noise. So let's put this in. So we ask for the probability AI plus N minus AJ smaller than AI plus N minus AI. AI will cancel out here. Arrange the first one, P. Yeah, I want to sort it a little bit, like get the noise separately and our values AI and AJ as N plus AI minus AJ. Then here we just get the Euclidean distance or the norm of this noise vector. Just notice that lecture slides, I use the powers instead of the norms. Instead. Also, this can be used. If the Euclidean distance is larger, also the Euclidean distance square will be. This just helps us later on dealing with this random variable. Let's write this once more. So this is the same as the probability asking for the squares smaller. Next, we want to evaluate this evaluate Euclidean distances. Vectors. It's basically the same as saying the probability Yeah, it's basically the sum over the squares of the difference of these two guys. So let me see. Sum. Let's write it back. So the norm vector n will be the sum of the individual elements square. So, and basically here we do the same. So the individual element square, sum here, r being 0. We have n elements, so to n minus 1, over our individual elements square. So this will be ni. Now be careful, this is now the scalar, the ith element in my vector n. Plus a. Oh wait, r is our index, it's the rth element. Here. A ir minus a jr so the rth element in my vector ai and the ij, and this one squared. And this should be smaller, sum being 0 to n minus 1 over the elements of my noise vector squared, nr squared. Okay, still the question is the same. What's the probability that the noise is such that this condition will be fulfilled? And if this condition is true, if this is smaller, this left-hand side, then we will get the decision in favor of AJ instead of AI. Now we just need to calculate this a bit further, simplify it, see how we continue. It's the probability. Now let's solve this square here inside the sum. R being 0, n minus 1. Yeah, the expression squared, that's like the first guy squared, n square, plus 2 times the first one times the second one, plus 2 times nr, ai minus ajr, plus the second guy square is a jr square. We ask for the probability that this is less or equal to sum over nr squares. A question from Kasan. Can you repeat what this norm here is? I put in 2 vectors, it's the Euclidean distance. And we get this vector norm by summing the squared elements of the vector. So in the Euclidean distance, and I put in 2 vectors here, I would subtract one from another and take the square of the difference in the elements. Then I will get distance. Okay, now let's see how things simplify. Is that we have this sum over here. So if we subtract the sum over the NR squares from both sides, it will disappear. There will be a 0 instead. We write this P, sum being 0 to n minus 1 over, let's bring here this mixed expression, 2 NR is AIR minus AJR plus sum inside the sum, so I can also write this as two sums. 0, it's just rearranging the order of summation. AI is AJR less than 0. So now I simply bring 1 to the other side. This is the definition which we will proceed with, the same as the probability that the sum being 0, n minus 1. So I will bring the 1/2 to the other side. It's 2 side. So here n AIR AJR is less or equal. So with a minus, this sum goes to the other side. Divided by 2, so it will be minus 1/2 sum being 0, n minus 1 over the difference of the elements. AI is AJR. We are still asking for a probability such that the left-hand side is smaller than the right side. And now we need to think about both of the sides. So on the right-hand side, we have AIR and AJR. So this can either be +1 or -1 or plus square root EC minus square root EC. This will be the more easy part to deal with. Whereas here on the left-hand side, we have the plus minus square root EC in our code sequence, but also the random value from the noise. So this left side will be a bit more difficult to deal with. This right-hand side, there we can easily think about what will happen or what can happen with these values. Let's look at this one first. So first note AI and AJR are element plus minus square root EC. AIR is not equal to AJR. Then AI is AJR. Yeah. For EC, yes, yes. Very good, very good. So of course, if they are different, one is plus square root EC and the other one is minus square root EC. So for example, if I have here a plus square root EC minus square root EC, we get 2 times square root EC, and the square will be 4 EC. Or the other way around, if the first one is minus square root EC, we get a minus plus square root EC, we get minus 2 square root EC, the square of it will be also 4 EC. So if they are different, we get 4 EC, and if they are the same, this is the other case that can occur. What do we get if they are the same? 0, yes, exactly. So those are the only 2 cases then that can appear here. Either the values are the same or the values are different. And actually, we can describe the number of values being different by using the Hamming distance between AI and AJ. So between code word AI and code word AJ, the H bits are different. So we can actually describe this. So for the whole code word, H, AI, J, different bits. So this means at the end, sum being 0 to x1 is a JR, where will be, yes, we get DH, AI, AJ times, where we have the different bits for EC, and actually that's already DH, AI, J, for EC. Align this that we don't lose the result here. So this one. So already from our general understanding, it is somehow obvious that the number of different bits will influence this probability. The more bits are different, the more unlikely it will be that I make this decoding error. This is already. Are there questions to this, according to this right-hand side? So then we come to the more difficult one, including this Gaussian distributed noise variant. This once more that here. So we are still interested in this pairwise error probability, mistaking AI, mistaking AJ instead of AI. once more. So on this side, we still have the sum r being 0, n minus 1 over nr, it's air, it's ajr. This sum is the probability that this sum is smaller than, including this minus 1/2, but here minus 2 bh ai aj times EC. So this is what we found. Yes. So let me repeat it. So here's the question again for probably for the understanding this error probability. So we ask for the probability that if AI is transmitted, so we say let's transmit AI, and then we ask for the probability that the decoder will come up with an estimated code word A hat, which is not AI, which is AJ. And we ask for the probability that the noise is such that AJ will be more similar to my received sequence Y as AI would be. So this is the case where we will mistake code word AJ instead of AI, which would be the correct one. Both, of course, must be a member from the set of code words gamma. Okay, coming to the more challenging part. This guy here. This is really a bit tricky. Start with this one, explain this one. So this NR is a Gaussian distributed random variable. With variance sigma square being n0 or standard deviation which is the square root of the variance sigma square root n0. So, and if we multiply such a random variable with a constant value, this multiplication will basically scale standard deviation. So this variable is scaled with this AIR minus AJR. We already know this can either be 0, values are the same, or it can be 4 EC, or it square root EC if they are different. Need to be careful, here's no square. But this will scale. Standard deviation. And we need to know some more things about variables now. So if we have some Gaussian distributed random variables, we will of course, again, get a Gaussian distributed random variable, and actually the variances will sum up. So this could now be also explained in detail, but just imagine the Gaussian distribution from one of the random variables. We know if we sum random variables, the probability density functions will convolve. So if I sum Gaussian random variables, I get convolutions of Gaussian distributions. And if I convolve a Gaussian distribution with a Gaussian distribution, it will be Gaussian distributed again, just the variance will be larger. So the variances will sum up. So sum of Gaussian distributed random variables this means the variance will be the sum the individual variances. Think about the variance first. Variance of sum. So it's the sum of the variances (0 to n minus 1). Yes, so the standard deviation of our noise process, NR, this was square root n0 half. So use some color to highlight this. NR. This is scaled by this difference between the elements in the vectors AI and J. AIR is AJR. Deviation. But we need to sum the variances and not the standard deviation. So this means we need the square of the standard deviation to be summed up. Square standard deviation. It once more clear, just to avoid that you mix it up. It's now not expressing the sum differently. It's something else. It's expressing the standard or the variance of the random variable that is basically formed by this sum over the Gaussian random variable. Let's underline this. We calculated here the variance of the sum. It's not rearranging the sum or anything, it's different. And we can simplify this somehow more. So you see n0 half is independent of r, so we can move it in front of the sum with the square. It will be a n0 half. It's the sum over air minus ajr square. And this we know from before. This is equal to, now again, it's important how many bits are different. dh, different bits between ai, aj, and times 4ec. C before. Yes. Okay, so here was the question to explain again the variance of the sum. Okay, so we have a process here containing these samples, these noise samples, NR, and we sum over several values NR here. So we have N Gaussian distributed values here, NR, and we ask for the variance of the sum. Let's explain it with some drawing. So we have N being N0, N1, up to N minus 1. Gaussian distributed. Gaussian distributed. Standard deviation N0, huh? And now we know from basics of stochastic processes that if I sum N0 plus N1 plus N, we need to convolve distributions. At the end, we will get also a Gaussian distribution, but wider. It's right here, variances will sum up. I cannot draw the variance in here because here it's actually standard deviation. Variances will sum up. Just take this as side note. Basics on stochastic processes. If I have a sum of Gaussian distributed variables, due to the convolution of the distributions, it will turn out that the variances add up. Our adds up basically. We have a note here from some students. And the last step, C. Yes, of course, we missed the N0 half. Good. 0 half. Or questions related. So right-hand side, basically have a constant, so we can calculate this. If the Hamming distance between these two code words. And on the left-hand side, we know now we have a Gaussian random variable with this variance. So this is basically all we need to know. Calculate now this probability. Let's come to the next page here. Again, this once more. It's pairwise error probability of staking AJ instead of AI. This is the probability. Actually, I rearranged it a bit by multiplying with -1. So this can be done. Get the minus here. Sum r being 0, n minus 1. nr times AIR is AJR. And if I multiply with -1, this will turn larger than HAI J times EC. Gaussian random square, and here this is basically just a constant. So we need to answer the question. What is the probability that the Gaussian random becomes larger than the constant? This means at the end we will have to integrate this Gaussian distribution from this constant value to infinity. So we will need somehow again an integral over a Gaussian function. And of course, this can be expressed by using the Q function or the complementary error function. So answer, we need to integrate Gaussian PDF probability density function easily described by saying Q function and there actually I provided again the definition of this Q function. Starting general here. It's the probability that Gaussian random variable x minus its mean value divided by its standard deviation will be larger than certain constant alpha, where x is normally distributed mean value y and variance sigma square. So actually, if I subtract the mean value and divide by the standard deviation, I get a Gaussian distributed random variable with unit variance and mean value 0. So this here on the left-hand side will be 0 mean unit variance. So this basically minus mu minus the mean value divided by the standard deviation, this normalizes a Gaussian distribution. And actually, let me also provide you this Q function, Q of alpha, well, 2 is the integral from alpha to infinity e to the power of t square. So notice this is here exactly the Gaussian distribution having unit variance and mean value 0. Now applying this to our problem, so we know the standard deviation, sigma. This is what we found out one page before. 2 EC and 0 EC, and somehow the distance EH AI J. This was the variance, and the standard deviation is the square root of this. And now I just bring this normalization in my equation up here. So saying P AI getting mistaken as AJ. It's the probability. I normalize this random variable, here by dividing through the standard deviation. And of course, if I divide this side by a constant, I also need to divide this side by the same constant. So this is how we get here the next expression. So we divide by standard deviation, 0 C H AI J, and we divide our variable here, sum of any random variables, NR AI R A JR. And of course, if we divide one side, we also need the side by the same constant N0 C BHAI J. And here we have the constant HAI J is EC. And let me use again some color easy for you to understand. So this normalized Gaussian random variable, this is what we got. By dividing through standard deviation here. And asking for the probability that this is smaller than a certain constant alpha. This here is this constant alpha. This will be the argument of the Q function. Subscript C subscript. Yes. So this here is EC. Okay, thank you. So some things will cancel out here. Notice if I write the equation on top as square root of this times square root of this, some things will cancel out. So, let's see. It's running out. So let me write this here. So notice this is Q. The argument is this green guy. And if we simplify the green guy, cancel out everything, we get a 2 HAI J and a C divided by N0. This is what remains if I cancel out the rest. This is actually the result that we wanted to show. So the probability of mistaking AJ instead of AI can be calculated by the Q function. And notice what it will depend on. As we already said before, the more different the two code words are, the more unlikely will it be that this mistake occurs. And the larger the signal to noise ratio, also the more unlikely will it be to make this mistake. So from our engineering point of understanding, of course, this makes sense that the dissimilarity between the two code words will influence this probability and the signal to noise ratio will influence this probability. Now we could actually also calculate this for certain values. For our example, see, did I do this on the lecture slides? Otherwise, we can do this. Yes, actually, I did this on the lecture slides, where we will continue next time. So there I calculated actually the probabilities of making certain mistakes here, decoding mistakes. But I think for today, this is a good result. So we know now how we got this so-called pairwise error probability of the probability of mistaking exactly one specific code word instead of the one that we actually transmitted. You could already think about how the story can continue. Of course, there's not only one error that could occur, also different errors could occur. And overall, we need to have a look at all possible code words, all possible mistakes that can occur. So this will be the way to proceed next time, see how to extend this even to the more general. Okay, are there questions for today? Okay, so then that's it for today. Thank you again for your attention. enjoy the snow outside and yes, have a good time studying. All right, goodbye.